Hello, everybody. Today we are going to discuss the maximization optimization problem subject to nonlinear constraints. So for doing that, we have a math model. We would like to maximize A, which is the width multiplied by length multiplied by height of a box, and we would like to find out the area, and we want to maximize with the variable value which we would like to take for W, L, and H. And the constraints are 2 into width into length plus 2 into width into height plus 2 into width height into length. These addition of these values should be less than or equal to 30. And our width should not be more than 3, our length should not be more than 6, and our height should not be more than 2, and all of them should be positive value. We use a sequential quadratic programming algorithm with this same fmin-con solver of optimization. SQP represents the state of art in nonlinear programming methods based on quadratic approximation of Lagrangian function. And the algorithm attempts to minimize the merit function subject to relaxed constraints, which leads us to feasible solution. This algorithm combines objective and constraint functions into the merit function. So let's first create the objective function, then nonlinear constraint file. And these two files, once it is created, will come back here and develop the remaining things. So let's go to the objective function first. So if this is our math model, which is same discussed here, right? Just referring it here. So we should write the 3 values which we are getting from X, and we are computing Y, and this value has to be maximized. So we need to put a negative sign ahead of it. Then we develop a nonlinear constraints. So considering these model, we have to take care of this constraint. With these all constraints can be managed by simply specifying the bound values, lower bound and upper bounds. But this is what is significant constraint we have to take care in this function. So we define again C and C equal, where nonlinear constraints will be bringing X. First value is given to width, second value is given to length, and third is given to the height. Then we compute C, where this value, because it is the other side of the less than or equal to, so we can put here negative and then put 30. And then CEQ will be filled up based on this value. So non-equality constraint. Once these two functions are ready, we come back here and then we start developing our code. First, we define the function, which is specified at objective function here, right? We define the lower bound and upper bound. So we can see that 0, 0, and 0. So minimum we have started with 0.1, 0.1, and 0.1. And here upper bound is 3, 6, and 2. So 3.0, 6.0, and 2.0. We define A, B, A equal and B equal because nonlinear constraints are there. And we give the initial value of x0 as 0.1, 0.1, and 0.1. Followed by nonlinear constraints, we are defining what is specified at our file, nonlinear constraint.mlx here, right? Followed by our options. So in the options we are defining, we are using the solver of fmin-con. We want to display the iterations. Our algorithm is SQP. We would like to plot the function using these 3 options because we want the plotting of X value, fitness value, and the first order of optimization. So then we simply call to fill the values of X equal to fmin-con, pass on the objective function, initial value A, B, A equal, B equal, lower bound, upper bound, constraints, and the options. Once we pass on these things, we can explicitly print the values of W, H, and L optimized value, and we print those values. if we, instead of putting X, we can also put a specific output we expect. That is X fitness value, exit flag, and the output. And I've kept the same values here, which lies here. So any one line you can put, that's why I've kept it comment. You may use this one or this one, up to you. So let's run and check how it works. The function is now getting iterated. And we could see that we have got the width, length, and height values here. Current point, 3 variables, right? The function value is obtained to be minimum here and maximum here. So first order optimality, if we see that, we can see it is here and the value is specified. So we go in depth by observing the iterations. So let's observe the results. If we see the results here, the function objective function is coming from objective function file. We have the number of iterations 12, right? The function count is executed approximately 52 times. This fitness value indicates which is going where, right? This is the feasibility stating most of them are in the tolerance other than 1, 2, and 3. All other values are 0, which is abide with the constraints. The step length is 1. Normal steps values, first order optimality. So now if we observe the results, we can see the optimum value of width, length, and height is presented here. We can see the current functional value, and then we can see the first order optimality also. So the local minimum found that satisfies the constraint. Optimization completes because the function value is non-decreasing in the feasible direction, right? So within the value of the optimality, tolerance and constraints are satisfied to within the value of the constraint tolerance. So then we are stopping the criteria and we have got the 3 values, W, L, and H for maximum values, that is 2.35, 2.35, and 2.00. So that's how we can perform the maximization, nonlinear constrained optimization using fmin_con and using the similar results. We end our video here. Thank you.